Hey everyone, welcome to the third video for section 3.1. In this video, we're just going to be doing some examples of solving linear, homogeneous, second order constant coefficient equations. We'll do two examples, one just solving for general solution, and one that involves solving an initial value problem where you actually have to plug in for the conditions at a certain point. All right, so let's go ahead and jump into that. Just two quick examples for this video. So for our first example, we're going to be solving for a general solution without having initial conditions. So here I want to find the general solution. 2y double prime plus 4y prime minus y equals 0. So we saw in the last video how we solve these equations. So the basic steps are step 1, find the characteristic equation. Step 2, find its roots. And then step 3, write your solution as constant times e to the root 1t, constant e to the root 2t. At least in the case here, we are going to have real and distinct roots. So step 1 is characteristic equation. Now you could go plug in e to the rt, take derivatives and solve, but if you see what happened in the last video, all that happens is the y double prime becomes an r squared, the y prime becomes an r, and the y just becomes a 1 to get your characteristic equation. So in this case, our equation is r squared plus 4r minus 1 equals 0. That just came from the y turns into a 1, the y prime turns into an r, the double prime turns into an r squared. That's all it is. This is really, really easy. And then step 2 is find the roots. And here this is just quadratic formula, unless it factors. If it factors, just factor it and you're good. But if not, quadratic formula is what you're going to want. So in this case, we're going to use quadratic formula. R equals negative 4 plus or minus the square root of 16 plus 4 minus 4ac. A is 1, c is minus 1, all over 2 times 1. So I get a minus 4 plus or minus the square root of 20 over 2. Root 20 is 2 square roots of 5 because it's root of 4 times root of 5. So my r that I get is negative 2 plus or minus the square root of 5. That looks nasty, but that's good. That is fine. There are two roots. They are both real. So I can write my general solution out. And all I do for this is I just write y of t equals c1 times e to the r1t. So just pick one of the roots. I'll pick the positive one first. Minus 2 plus root 5t plus c2 e to the other root minus 2 minus root 5t. And that is it. We are done. That is how you find the general solution for an equation like this. You do your 3 steps. You find the characteristic equation, which just involves placing derivatives by powers of r, more or less. You find the roots by the quadratic formula, or by factoring, and you write your general solution out just like that. All right, we good? That's example 1. Now for example 2, we're going to have initial conditions. So find the solution to y double prime plus 3y prime plus 2 to y equals 0, y of 0 equals 1, y prime of 0 equals 4. Now what you'll notice here is I gave two initial conditions here. We're going to see in section 3.2 why we need that. But basically you need the same number of initial conditions as the order of your equation. So specify two conditions here at t equals 0 will allow me to completely determine my equation from that. So let's solve this. So step 1 was find the characteristic equation. So I get an r squared plus 3r plus 2 equals 0. And I'll notice right away that this factors. This factors as r plus 2, r plus 1, which means step 2, what are my roots? The roots are r equals minus 1 and minus 2, which means my general solution, y of t equals c1 e to the minus t plus c2 e to the minus 2t. which was what we needed to do for the last problem, but this one just works out quicker because it factors nicely. Now we're not quite done yet because we still have to meet our initial conditions. So let's write those out in terms of equations and see what we get. So first, let's find out y prime of t is. So y prime of t is going to be minus c1 e to the minus t minus 2c2 e to the minus 2t, just by taking derivatives in t. So now we can plug in t equals 0 and see what we get. So if I plug in t equals 0 to both of these, I get that y of 0 is going to be c1 e to the minus t is 0 plus c2 e to the minus 2t is 0. And y prime of 0 equals minus c1 e to the minus t is 0 minus 2c2 e to the minus 2t is 0. And by my initial conditions, I want this to be 1 and this to be 4. Now at this point, you can solve the equation however way you'd like. To me, it looks easy. I'm just going to add the two equations together. And so I get 5 equals 0 minus c2. So c2 equals minus 5, which then tells me that c1 equals 6, because I need the first equation. I have to add the two together to get 1. And now if I plug in those two numbers, I get my specific solution. Y of t equals 6 e to the minus t minus 5 e to the minus 2. Box that in orange as our final answer. So these equations are not hard to solve. They follow a pretty strict procedure as to how you solve them. You take your original ODE, you find the characteristic equation that corresponds to it, you solve that for the roots r, and then you write out your equation. And then if you need to find initial conditions, you just plug those in and see what you get. All right, that's it for this video. There's two examples of how to solve these second order linear constant coefficient equations. In the next section, we'll go forward to do some more of the theory about it. Unfortunately, we have to do more theory, where we talk about sort of why we know this gives us all the solutions we could possibly get to our equations. All right, thanks a lot for watching, and I will see you in the next one.